Look, it's something property related to the kinetic theory of gases. Now what does it say? It says the ideal gas in a closed container is slowly heated. Now the container is closed. The volume is constant. And as the temperature increases, which of the following statements are true? So you need to verify individual options one by one. The first thing, mean free path of the molecules decreases. It will not change because the number of molecules that's same, the volume is also same. So in that case, the mean free path that will not change, right? And the expression of the mean free path is going to be 1 by root 2 pi d square into small n, where small n is of course number of molecules per unit volume, not to confuse with number of moles. Since the number of molecules is same, the volume is same, and d is the diameter of the molecule, that of course does not change, so option number A would be inconsistent. And after that, mean collision time between the molecule decreases. That's right, because you see the average speed will increase with temperature. The mean free path is same, so of course the mean collision time that has to decrease. The mean free path remains unchanged. Okay, got it. The mean collision time remains unchanged. That would be incorrect. So based on this, we need to see where is the correct one. Let's sort out, and you could see it's option number 3, B and C, they are correct. A and D, that's incorrect. Let's go for the next one, and that is something like this. You could see a heat engine is involved with the exchange of heat, so much so that's given. Wherever the positive sign of heat is there, that means it's a heat absorbed. And the negative sign of heat means that's heat evolved. And that completes one cycle. We need to calculate the value of this Q, the magnitude part, and the efficiency, that's given as 50%. This is again a straightforward one. Efficiency is 1 minus magnitude of Q evolved divided by Q absorbed. Remember, Q evolved is characterized by the negative sign, but we need to put only the magnitude. That comes from the derivation of formula. And this efficiency, that is half in terms of fraction, and that is equal to 1 minus, what will I get upstairs? Q plus 40, and downstairs that's 1915 plus 125. That's it. And you solve this, you're going to get the magnitude of Q as 980 joule. Option number 1, that's the correct one. Let's see question number 6. Question number 6, from atoms and something related to frequency emitted upon transition from one state to other, that has to be computed. But there is a condition given where the principal quantum number is much greater than 1. And the transition is happening from n plus 1 to n. Let's see the calculation here. All of us know that the frequency of emission is, directly proportional to the energy gap. And here the energy gap, because we all require only the proportionality, so I can write n square minus 1 by n plus 1 whole square. Okay, now let's see the calculation, and we'll finally put the condition that n is much greater than 1. So this comes out to be 2n plus of 1 divided by n square n plus 1 whole square. Now just pay attention, how do we put the condition? Because n is very much greater than 1, this particular 1 can be fairly neglected, and even this 1 can be fairly neglected. So upstairs n, downstairs n4, so ultimately this is going to be 1 by n cube. And there it goes, option number 3. A good one, worth doing. Let's go for the next.